All right, in this video, I'm going to review the answers to these 4 review questions, as well as go through some examples of compounding interest problems. So for the first reflection question, I asked, as the number of compounds increased, what happened to the value to 7 decimal places? So not necessarily the dollar value that you ended up with, but the value of the total to 7 decimal places. And what you should have been able to see from the video was that as you were increasing the number of compounds, that value to n decimal places was increasing. Right, so this increased, but it didn't always increase at the same rate or at the same amount. So it increased, but slowed down as it was increasing. Right, beyond a certain point, you weren't even getting 1 more cent being added on, despite increasing the number of compounds considerably. So the second question here, just kind of relating this back to a limit. In this case, which variable is approaching infinity? This is set up to have n approaching infinity. So we're looking at a limit of a value as n, or the number of compounds, is approaching infinity. And this is really the only way to find that maximum value, because you can't plug infinity into the function, but you can set up a limit to see what happens to the function as you approach infinity, or as you get closer and closer to infinity. As n continues to increase, what do you think will happen to the value of the compound interest function in this case? So you have kind of 2 options here. You are either going to continue to increase all the way to infinity, or you're going to approach a specific value. And in this case, what actually ends up happening is we approach a specific value. And I'll get to what that specific value is after talking about the next question, or kind of to answer the next question. Because this is actually ends up being a very important value in mathematics, and one that we are going to be using throughout this unit. So this actually does end up approaching a specific value, and you can probably tell what that value is, or close to what that value is, based on what you've seen so far. So the last question here is, do you think the dollar value will ever reach $2.73? So with the rounding, that dollar value ended up at $2.72 for all of the compoundings that you did. But as we approach infinity, right, we know that this is kind of continuing to increase, but we don't necessarily know where it is increasing to. So the answer to this question, and this was just asking you for kind of a speculation here. You may have run a couple more scenarios, adding more compounding. But what actually ends up happening here is this does not reach 273. We don't quite get to 273 in this problem. The highest we get to is that 272 value. Okay, so I want to quickly talk about these last 3 problems here, kind of combining these into what this is really saying. So we have our compound interest function, and the way that you set this up would be the total is equal to 1 times 1 plus 1 over n, your number of compounds, right, to the n times t, which in this case, our t value is 1, right? T equals 1 because we're talking about 1 year. So what we're really doing in this whole problem is we are evaluating this limit. So the limit as n approaches infinity of 1 plus 1 over n to the n. I took out the green n there just because it doesn't change the value here, right? Multiplying by 1 doesn't change anything. So this is kind of what our table was evaluating, right? And this is equal to a brand new number that you have not necessarily seen before. And this is the specific value that we approach. Okay? The specific value we approach is the number e. Okay? Now, e is very much like pi. Okay? It represents a specific value. So here, e is equal to approximately 2.718281845 continued. If you look this up on Google or find the E button on whatever calculator you are using, you can see that this constant has this value. E is Euler's number. And I know that's a weird way of saying that name, but that is how his last name is pronounced. Euler is a very prolific mathematician. He's one of the best mathematicians of all time, just in terms of how many fields he influenced and how many interesting problems he solved. But interestingly enough, Euler's number was actually not found by Euler, but instead found by Bernoulli when he was actually investigating this exact same problem that we just did. So discovered by Bernoulli. So E is also very interesting because it's one of the first constants, or actually I think it is the first number that was defined by a limit. Okay, so this right here is actually the definition of E. And we're going to see a whole bunch of different places where E comes up. A lot of times it's in population growth, but where it's going to come up most immediately for us right now is in this specific scenario. So I want to go back to kind of thinking about what question we were trying to answer by taking all of these different compounding values. And essentially we were trying to maximize compounding. And in order to maximize compounding, essentially what we are doing is not just compounding every certain amount of time, but compounding all the time, right? Infinitely many times over a certain period of time. Okay, so to maximize compounding, this is called continuous compounding. And it actually ends up having its own unique formula. And this is because, again, we can't enter n equal to infinity for continuous compounding, right? We can't use n equal to infinity in a formula. So the continuous compounding formula ends up like this. T total equals principal times our new value e to the r t. A lot of people call this the PERT formula, and you can pretty easily see why they call it the PERT formula. So for continuous compounding, when you want to compound all the time or use n equal to infinity, e is going in instead of the 1, right? So this is like 1 plus 1 over infinity to the infinity, right? Instead of writing in that 1 over infinity to the infinity, we use the limit of this to write e. So now let's actually go ahead and use this continuous compounding formula. So this is now our continuous compounding formula, and we also have our compounding interest formula that we talked about in the last video. So let's see how this actually works out. All right. So you are lucky enough to find a savings account that earns interest continuously. We're very happy about that. Again, no limit on how many times we are compounding. The rate on this account is 4.8%. Knowing that this is a great deal, you're going to invest all the money you have, which just so happens to be $1,846.55. How much will this account be worth in 20 years? Okay, so because this is continuous compounding formula, continuous, you know that you are going to use the PERT formula for this. So P e to the r t. So go ahead and see what value you get for your brand new account in 20 years. So pause the video now to solve this out. Okay, hopefully you had an opportunity to plug in a few numbers into this formula. But if not, here is what we're going to end up with. So our total in this case is going to equal 1,846.55 times e to the r, and in this case r is 0.048 times the t value here, which is 20 years. You can go ahead and enter this all into your calculator all at once. If you do so, just make sure that you put parentheses around your exponent, just to make sure that it doesn't raise e to the 0.048 and then multiply everything by 20. Again, sometimes calculators don't do order of operations in the way that you intended them to. The other way that you can do this is to put this into your calculator first and then multiply that by 1,846. Either way, you should end up with a final value of $4,822.63. So that's with continuous compounding, we end up with this amount of money in our account. Okay, second example. And this one is not going to use continuous compounding. We're going to go back to our just compound interest formula. So I'll just write that out again, just so that you have it. So this question is actually one that is really good to know the answer to here, because it directly applies to a situation that may come up in your life. So this is talking about an unsubsidized student loan for $12,000 during your first semester of college. Quick background on unsubsidized loans. They do not require you to make payments while you are in school, but they will accrue interest. Okay, so that means that the amount that you owe the bank is going to increase as time goes on. So they give you the money, but then they say you're going to pay all that $12,000 back plus this interest. So it kind of works in the same way that a bank account would work, in that the amount is increasing over time, but this one's not really working in your favor. Okay, so let's look at I'm going to give you a chance right now to calculate this out. So pause the video to take a second to calculate how much you would owe through this scenario. Okay, hopefully you had an opportunity to work through this. I'm going to highlight my important values here. We've got $12,000, that's my principal. And then this is 1 plus the rate, which is 0.0575 over daily compounding. Just for simplicity's sake, we're going to say this is 365 days a year. We're not going to say that this is 365 and a quarter days a year to factor in leap years. If it's daily, I'm going to say that you should just be using 365. It takes you 4 years to graduate, so you graduate right on time. So that's your t value, and that's to 365 times 4. So when we go ahead and we calculate this out, we get, let me see here, 12,000. One plus 575. Sorry, I didn't have this one plugged into my calculator already, so I'm calculating it out now. And again, just as a note here, it's important to put that exponent in parentheses as well. This should come out to a total of $15,102.93 or 92 cents. That 0.6, the bank is probably going to round that up for the purposes of a loan here. So you can see that in 4 years, you're going to have accrued over $3,000 in interest just by the loan kind of sitting there and not being paid down at all. So that's how much you would owe starting after graduation. All right, one more question, and this one's asking a little bit different type of a question here. So a friend tells you that they have just received an inheritance from a long-lost relative, and the inheritance itself is worth $5,414.63. Your friend knows that the account was opened 80 years ago and had a rate of 5% interest compounded monthly. You and your friend are curious how much the initial deposit on the account was. Can you find out? So pause the video now to see if you can do a little bit of detective work using the formulas that you have at your disposal to find that initial deposit for this account. Okay, so in looking at this problem, the first thing that I'm going to kind of point out here is that this is compounded monthly. So the formula that I'm going to be using is not PERT, but it's going to be the P times 1 plus R over N to the NT formula, and that is going to equal my total value. So let's go through now the problem and highlight the information that we have. So the first number that we are given here is actually the total, right? This is the final amount. This is what the account ends up being worth. So $5,414.63 is not our principal, because that's what we are trying to find out, right? The initial deposit is unknown. So the initial deposit is still P, right? This is the unknown initial value. All right, so we should have the rest of this information here for us, right? So this compounded monthly means n equals 12. So 1 plus something over 12 to the 12 times something. My rate here is 5%, so that's 0.05. And that is 12 times the time here on this account, which is 80 years. So 12 times 80. Okay, so now we need to find this unknown initial value. And in order to do that, we're going to be solving this algebraically. And kind of the easiest way to visualize this happening is to figure out first, what is this value, this parentheses raised to the power. So what I'm going to do is I'm going to go in to my calculator, I'm going to plug in 1 plus 0.05 divided by 12, close my parentheses, raise that to the 12 times 80 power, and I'm going to get this yellow value as 54.146305432. The less that I round off here, the more accurate my final answer will be. Just as kind of a general note, do not round until the end. Okay? The more you round off in the middle, the further off your final value is going to be. So it may be a pain to write this all out, but it is being done for the sake of a more accurate final value. Okay, so this becomes P times 54.1463, etc., equals $5,414.63. So now, in order to get this p-value alone, I have to divide by this 54.146 ... value. And this is a way that you can kind of abbreviate. You don't have to write out every single number, as long as you know you're using the whole number to do your actual operation. So now all I need to do is take my initial value, or my final value, $5,414.63, and divide it by this final value. And what I'm going to end up with is that my p-value here is going to equal $100. You may get like 99.9999 for this. That is definitely close enough to round up to that $100 value. Definitely the nearest cent there. All right, so those are kind of one specific application of compounding interest. Most oftentimes, or a lot of times in the real world, compound interest comes up in the context of money being held for a loan or being invested. We will go into more different applications for compound interest. We'll get into population growth, viral spread, exponential or radioactive decay, all sorts of other interesting applications. But this is one of the most often used purposes for compound interest. So your homework is a worksheet that has a whole bunch of compound interest problems. They have problems both where you need to find the final value, so you need to get to the total, or you need to get to the principal, just like we did in this problem, and that will contain both compounding a certain number of times per year, as well as compounding continuously. So you need to know both of those equations to be successful on the homework here. I'm asking that you do one per row on that homework. Good luck and enjoy your